All right, so today we're going to be looking at what's known as the ideal gas law. A lot of people refer to this as Pervnert, but basically it's a way to bring in the moles. So if we remember, pressure and volume are indirectly proportional, and pressure and temperature are directly proportional. Indirectly means that the pressure goes up if the volume goes down. So they kind of go opposites. If the volume goes up, the pressure goes down, right? The temperature, if we were related to pressure, if the pressure goes up, if the temperature goes up, that's because they're directly proportional. If the volume goes up, if the temperature goes up as well. So we need to figure out how moles is revolved in it. Well, if we put more moles, which is in, or more number of particles in there, then the pressure goes up. If we put more particles in there, the volume goes up. So according to pressure and volume, the number of moles also is directly proportional. As the number of moles go up, these two would go up. As the number of moles go down, they would go down. So that's how we kind of set up that formula. So if we set all this up, we can find what we would call basically an R, or it's called Riley's constant. And basically we could, using this R, we could figure out any one of these with the other three variables. So if we imagine STP, standard temperature and pressure, pressure is 1 atmosphere, temperature is 273 Kelvin, so it's standard temperature pressure, and we measure out 1 mole of gas. 1 mole. I'm just doing this as all exacts, so I don't have to worry about it. So I'm going to go ahead and put 1.5 there, whatever. What would the volume be? Well, we said 1 mole of any gas. 1 mole of any gas at STP takes up 22.4 liters. So if we put that 22.4 liters in there, then we can find this R constant. So let's go ahead. P is 1 atmosphere. V is 22.4 liters. T is 273.15 Kelvin. And this is 1 mole. 22.4 divided by 273.15.
It's about 0.082.
So 0.082. Most of the time people said 0.0821. So they may know more decimal places on this or on this. Let's try this. 22.4 divided by 273.
It's about 0.08205.
So they probably don't bother. They just use 3 significant digits with both of these, and then they put 0.0821. So that's the one that we're going to use as our constant because it's the most common one in books, textbooks, and stuff. Now the trick to this, though, is that you have to have atoms, liters, over Kelvin mole, because none of these cancel out. None of them cancel out. So that comes down to what we call the Pervnert, or the ideal gas law. This is based off of Avogadro's principle. He stated that a volume of a gas is directly proportional to the number of moles of that gas at constant pressure and temperature. So if you have pressure and temperature constant, if the moles are constant or equal of 2 gases, then they would take up the same volume. Now, since we use different pressure units, you can see that each of these constants, these are the 3 constants, most of the time I will just change it to atmospheres and use 0.0821 versus memorizing multiple ones. So keep that in mind. Let's try a problem with it. Let's go to page 14, which is your homework for tonight. I think 14 and 15, or the one that says ideal gas law at the top of it. So it says, how many moles of oxygen is present at 256 liters, 1.05 atmosphere, and 18 degrees Celsius? 18 plus 273.
The answer is 291.
291 Kelvin. So we want to find out how many moles there are. That's our N. So if PV equals nRT, then N will equal PV over RT. It'll cancel out on that side right there. So then let's plug these in. Pressure is 1.05 atmosphere, right? And volume is 256 liters. R, 0.0821 liter Kelvin mole atmospheres. And T is 291 at 0.15, whatever. 1.05 times 256 divided by 0.0821 divided by 291.15.
The answer is about 11.2452.
So that would be 11.2 moles. That's it. Basically, you just go through and rearrange the equation and then solve for it. Taking note of this one, it says what pressure in atmospheres, so you'd use the 0.0821 for the R. But if it said what pressure in millimeters of mercury, you'd use 62.4, or you could change it at the end from atmospheres to millimeters of mercury, or however you want to do it. None of that is a big deal. Number 7 is kind of fun. It says density is defined as mass divided by volume. For a gas, density is usually labeled in grams per liter. If you have 7.50 grams of neon in a container at 25 degrees Celsius and 1 atmosphere, and calculate the mole of neon. So you don't need the ideal gas law for this. So 7.50 grams of neon from the periodic table of elements, every 20.17 grams of neon is 1 mole of neon. 7.50 divided by 20.17.
That would be about 0.3718.
0.3718, and that's with 3 significant digits. Moles. It says then calculate the volume of the container. Well, now we have N, we have P, T is 298.15. This is our N. We want to solve for V. PV equals nRT. Right? So 0.3718 times 0.0821 times 298.15 divided by 1.
The answer is about 9.1009.
With, again, 3 significant digits. And that is liters. So if we wanted to calculate the density, we could take 7.50 grams and divide it by 9.1009 liters. 7.50 divided by 9.1009.
It's about 0.824.
0.824, 3 significant digits, grams per liter. So by knowing the mass here, or by knowing the moles, we can find the density of the gas if we also know the volume. We could have been given the moles and then find the grams using the molar mass, and then taken that, found the volume, and then divided that by that to get that again. So keep that in mind. That's what they want you to do for 8 and 9 here to finish up 15. Excellent. Thank you.